Today, our group, comprising of Leslie, Hansen, Famous, Humphrey, and Frank, is thrilled to present our research on discrete geometry in machine learning. In this presentation, we explore how discrete geometric methods such as convex halls, the Voronoi diagrams, and simplicial complexes can significantly enhance machine learning tasks. These methods offer innovative solutions to challenges in feature selection, clustering, and pattern recognition. Over the next few slides, we'll guide you through the objectives, methodology, and outcomes of our research. Let's dive in.
I'll be taking you through the introduction of our research. Let's start by talking about why we chose this topic. Machine learning has improved a lot over the years, but it still faces challenges, especially when working with messy, incomplete data. Traditional methods often have trouble understanding complex relationships in this kind of data, which affects their performance. This is where discrete geometry helps. Using shapes like convex halls, Voronoi diagrams, and simplicial complexes, we can better understand and analyze complicated data. These tools help us find patterns and connections that traditional methods might miss. Our research shows how these geometric techniques can make machine learning better. They help in 1. Feature selection. They help in 2. Clustering and pattern recognition.
Okay, so I'll be taking us on research objectives. Our research focuses on 3 primary objectives. The first one is performance assessment, to evaluate how discrete geometry methods like convex halls, Voronoi diagrams, and simplicial complexes compare with traditional machine learning approaches, tasks such as clusterings and then feature selections. Also, by comparing accuracy, robustness, and interpretability, we aim to identify where these geometric methods excel and where they might fall short. Moving on, we're talking on we're evaluating the scalability. And then to do this, we test the scalability of these methods on real-world data sets. How do we do this? Particularly to those with high dimensionality or noise. Data sets like MNIST provide a challenging environment to assess how well these methods handle large scale. And then the third one is integration into the machine learning pipeline. And how does this work? Finally, we aim to explore how these geometric methods can be integrated into existing machine learning workflows. Also, this involves analyzing their strengths and limitations and identifying opportunities for future improvement or complementary use alongside traditional algorithms. Yes, so we'll be moving on.
Okay, so moving on to the overview of the geometric methods we used in our research. Let's take the first one, which is convex halls. So with convex halls, they define the smallest convex set enclosing a data set. Convex halls are especially useful for feature selection, helping identify the most relevant points on the data set's boundary. They also play a critical role in outlier detection, providing insights into how data points relate to the overall structure of the data sets. Now, move on to Voronoi diagrams. Here, Voronoi diagrams usually partition the data space into regions based on proximity to a set of central points or generators. This makes Voronoi diagrams highly effective for clustering tasks as they organize the data points based on spatial relationships. These diagrams also find applications in nearest neighbor search and density-based clustering. So finally, we have simplicial complexes. Simplicial complexes generalize graphs to higher dimensions, capturing topological features such as holes, voids, and connectivity within data sets. A specific application of simplicial complexes is persistent homology, a technique that examines the evolution of topological features across different scales, revealing patterns not easily detectable by traditional clustering methods.
So our methodology was designed to systematically explore how discrete geometric methods enhance machine learning tasks. Here's how we approached it. So first of all, data selection. We choose 4 data sets. The iris data set, which is known for its simplicity and natural clustering structure. The second one is the wine data set, which adds complexity with 13 features and multiple classes. Then the biggest data sets is a higher dimensional data set representing handwritten digits. And the MNIST data set is a large-scale data set ideal for testing the scalability of those methods. Now, the implementation steps. After reprocessing the data set to normalize features and handle missing values, we apply geometric methods for feature selection and clustering. Convex halls were used to identify boundary points for feature reduction, and Voronoi diagrams and simulation complexes were implemented to analyze clustering outcomes and topological features. So the third one is the comparison, and these geometric methods were compared against traditional algorithms like K-means clustering and then support vector machines. And the fourth one is the evaluation metrics. To ensure performance, we focus on accuracy, silhouette score for clustering quality, adjusted run index for clustering consistency, and computational time for scalability.
So let's look at the results of our study. So the first of is going to be convex halls. These were highly effective in feature reduction, leading to improved model efficiency without significant loss in accuracy. And the second one that we look at is the Voronoi diagrams. They outperform K-means in clustering tasks, especially in data sets with clear group structures, by better capturing spatial relationships. And the last one that we look at is the simplicial complexes. These revealed robust topological structures, excelling in data sets like MNIST. However, they face computational limitations, particularly with large-scale data. Overall, discrete geometric methods demonstrated their potential to enhance machine learning tasks, although computational costs remain a challenge for certain applications.
We would be going to the discussion of our research. We will be looking at Voronoi diagrams, convex and sequential complexes, and also comparisons with traditional methods. So now Voronoi diagrams excel in clustering tasks, capturing spatial relationships more effectively than traditional methods. Convex halls enhance feature selection by identifying boundary points but struggled with scalability in larger data sets. Now, let's talk about simplicial complexes. These complexes provided valuable multi-dimensional insights but required significant computational resources, limiting their applicability to smaller data sets or optimized implementations. Compared to traditional method of machine learning approaches, these geometric methods, as you can see here, showed clear advantages in handling complex relationships in data. However, integrating them into mainstream workflows will require addressing their computational demands.
Okay, so in conclusion, our research highlights the potential of discrete geometry methods to improve machine learning. And then we have so many few points to discuss. This method enhances feature selection, clustering and pattern recognition by leveraging geometric and topological insights. Secondly, challenges like computational cost and scalability need to be addressed. And then future research could also focus on optimizing these methods and exploring additional geometric approaches such as alpha complexes or other topological data analysis techniques. And this is how far we've come with our research. Thank you for listening.